Yes, ma'am. I'm also online.
Might have started. Okay. So we had started with first part of your CPU architecture, third lesson. We had seen that the CPU has three components: the ALU, arithmetic logic unit, CU control unit, and register. We had seen the internal structure, that ALU contains shifter, complementers, which is used for performing complement and shift operations. Then we had seen that your Boolean logic and arithmetic logic performs your arithmetic and logical operations. We had seen that there's a component called as status flag, and now we are aware about what is that status flag: carry, parity, auxiliary carry, sign, zero, directional, interrupt, and trap. All these are what the status flag, and these status flags are there in each and every processor. Then we had seen that the internal CPU bus was used for connecting or communicating between your ALU and register, and the control unit is used to control the function of the ALU as well as the registers. Then we had started that there are different types of processors from 8085 till all the latest that we have today, out of which we had started learning about 80386 processor. So it is divided into three units: the bus interface unit, the CPU, and the memory management unit. So the bus interface unit talks about all the different buses which are there in 80386. It has 32-bit of address bus and 32-bit of data bus, which can be used as 8 bits or 16 bits in single. But if I want to use more than 32 bits, I have to make a use of a same bus twice. Then we had seen that there's an instruction queue where all the instructions are stored, but they are not executed, and the size of that instruction queue is of 16 byte. All the instruction which has to be executed goes into the decoded instruction queue, which is a part of a CPU. Then we had seen that the CPU executes all your instruction, and it has a part inside it called as ALU. CPU has two things: IU and EU. The IU is instruction unit, which starts decoding of the instruction, and your EU, the execution unit, looks after all the ALU operation. Then we had seen that the memory is managed into 80386 by using two things, that is paging and segmentation. If a data is in the form of paging, then every page has different page numbers, and the data is accessed through the page number. And if it is segment, your data is divided into different segment, and every segment has a segment number in order to access the data. Then we had seen that there are different registers in each and every processor. So we have registers in your 80386 are divided into user visible registers, control, and status register. Now, user visible register means those registers are visible, or the values of those registers are visible whenever we execute that assembly language program. So we had general purpose register, data register, address registers like segment, index, and stack pointer, and condition code register. The control and status registers were program counter, instruction register, memory address register, and memory data register. So your GPR, which was general purpose register, was used to hold the operands. Your data register were used to hold the opcode, that is the data. Your address register was used to hold the address, either in the form of a segment, index, or stack pointer. Then we had a condition codes called as status registers like sign bit, 0 bit, carry bit, overflow, and interrupt. Then control register program counter used to point the next instruction for execution. Whichever instructions are recently fetched were stored in instruction register. The address of those instructions were in the memory address register, and the exact data was in the memory data register. Then we had seen different registers of 8086. The GPR, that is general purpose registers, were of four types: AX, BX, CX, DX, which can be operated as AL and AH. That means AX entirely was of 16 bits, but your AL is 8 bit and AH is 8 bit. That is higher bits and the lower bits. So lower 8 bits, higher 8 bit is equal to 16 bits. Similarly, your BX, base registers, was divided into BL and BH. Your CX register, that is count registers, were also divided into two 8 bits, CL and CH. Last, your data register was divided into again two lower 8 bits, DL, and higher 8 bits, DH. Then we had also seen what is stack pointer, base pointer, source index, destination index, and instruction pointer. Then we had seen different segment registers of your address registers like code segment, data segment, extra segment, and stack segment. After that, we had seen the flag register, which is of 16 bits in case of 80386, where the bits which are empty are marked as 0. Your carry will be set. If the carry is generated, it will be set to 1. If it is not, will be set to 0. Again, if it is even parity, set it to 1. If it is odd parity, set it to 0. Auxiliary, if there is a carry which is of third bit, both set this as 1 or else 0. If entire result is 0, set this bit to 1 or else 0. If a number is positive, set D7 as 0, and if it is negative, set it to 1. Then if there is a trap, that is the highest priority, then that value will be set to 1, else it will be set to 0. If there is any interrupt, then the bit D9 will be set to 1, else it will be set to 0. Then D10, which is a directional, which is used to retry the data as lower bit to higher bit or higher bit to lower bit. And O is for overflow. So if a data is, or if the result is over, number of bits are more than the 16, then this bit will be set to 1. So with this, we had completed with the first part of our CPU architecture. Today we'll be doing the next part of the CPU architecture, which is the register organization of 80386. So we had seen the register organization of 8086. General purpose register we had seen index register, stack pointer, segment register, code segment, extra segment, flags register, everything were covered. That is both the user visible and the control and status. Similarly, we have registers also for 80386. So we'll be doing the registers for 80386 today. Okay. So 80386 has 8 32-bit general purpose registers. Now, how many general purpose registers were there in 8086? Only 4. Which were they? AX, BX, CX, and DX. Accumulator, base, count, and data. Whereas how many general purpose register does your 80386 have? They have 8 general purpose register. What was the size of general purpose register in 8086? It was 16 bits, used as 2 to 8 bits together. Whereas in 80386, since everything is of 32-bit, that is address and data bus both, therefore your size of the general purpose register of all the 8 general purpose register is how many bits? It is 32 bits. So it can either be used as 8 bits or it can be used as 16 bits. How we were using 8086 16 bits as 2 8 bits. Similarly, your 80386 general purpose registers can be used as 8 bits also and can be used as 16 bits also. All the 32-bit registers are called as extended register. Now, why they are called as extended register? Look into this diagram. If you see AX, BX, CX, and DX, this was there in 8086. Okay. All these 4 were of how many bits? 16 bits. But now your 80386 is of how many bits? From 0 to 31, which is 32. Okay. So your AX is now converted into EAX, which is what? Extended accumulator, extended base register, extended count register, and extended data register. So that E indicates extended, which means instead of 16, it is now extended to 32. So this AX is of 16 and these bits are another 16. So it can be used as two 16-bit registers. Two 16-bit register is nothing but one 32-bit register. Okay. So as it is written over here, it can be used as 8-bit or 16-bit. But how? Two 16 bits used together will form 32 bits. Are you understanding this?
Ma'am, it says we can also use it as 8-bit registers. So there will be 4 8-bit registers, right? So
Four 8-bit registers. Right.
so which will be higher and which will be lower, ma'am?
Yeah, there is, if you are using it as 8 bits, since the division is 4, so it will be 2 lower and 2 higher, like that.
Okay, ma'am, understood.
Understood? Huh. And if it is 16 16, 1 lower, 1 higher. Okay. And if you are using it as entire 32, we'll call it as EAX, EBX, ECX, and EDX. Why? Because it is extended, and that extended is how much extended? More 16-bit. So 16 plus 16 gives me 32 bits. Is that clear?
Yes, ma'am, clear. Thank you.
Okay. So the 16, along with this EAX, EBX, ECX, and EDX, we have something called as base pointer, stack pointer, and destination index. They are now extended to 32 bits: EBP, ESP, ESI, and EDI. Let me show you the diagram. Okay. So what is this? This is source index, SI. DI is destination index. BP is base pointer, and SP is stack pointer. So we had all these four for 16 bits in 8086. But now in 80386, again, since they are of 32 bits, so we have renamed it as ESI, EDI, EBP, and ESP. That is extended source index, extended destination index, extended base pointer, and extended stack pointer. Did you understand this? Yes or no? Okay, so everything which was of 16 bit in 8086 is now extended and renamed it as extended version and changed the bits from 16 bits to 32 bits. Okay, so see now, AX represents the lower 16 bits of 32-bit register of EAX. Okay, so the diagram which you can see over here, this AX is what? Lower bytes of extended 32 bits. This AH will be what? It will be the higher bits of the accumulator. Again, higher bits of base register, higher bits of count register, higher bits of data register, higher bit of source index, higher bits of destination index, higher bits of base pointer, higher bit of stack pointer. Okay, so again, this base pointer, stack pointer, source index, and destination index were 16 bits. Now they have become extended version with 32 bits. Do you remember we had segment registers in 8086? Yes or no?
Yes, ma'am.
Same segment registers are now extended into 80386. So code segment, stack segment, data segment, and extra segment, which were previously of 16 bits. Now they have extended and become how many bits? 32 bits. Along with that, we have two more extra segments in 80386 which were not there in 8086. Which are those? FS and GS. Okay. Now both of these bits are always empty unless and until you do not have a overflow or any other kind of function. What are those? That we'll be seeing in the detail ahead. But right now, just remember there are two more extra segments which were not there in 8086. Okay. There is a 16-bit instruction pointer. Now, instruction pointer was of 16 bits. Sorry, was not there in your, was of 16 bit in 8086. Now it is of 32 bits in 80386. So since it is 32 bits, so it will be named as EIP. What is that EIP? Extended Instruction Pointer. So if you want to remember this diagram, how are you supposed to remember? In 80386, we have general purpose register, which are same as that of 8086, but only difference is size. The size in 8086 was 16 bit. Now in 80386, it has become 32. So since it has extended, so they are now renamed with a letter E or a prefix E in front of each and every register. So instead of AX, we'll have EAX. Instead of BX, we'll have EBX, like that. Okay. If it is segment register, we had only 4 in case of 8086 of 16 bits. But in 80386, we have 6. All the 6 are added with a prefix E. And since we have added prefix E, so the size is also changed from 16 bits to 32 bits. Then we had instruction pointer of 16 bits in 8086. Now we have it of 32 bits with extended IP in 80386. The functions and all will remain same. Is this understood to you? Yes
Yes,
or
ma'am.
no? Everybody, girls?
Yes, ma'am.
Girls, are you okay? Now, did you remember we had flag register in 8086, which was of 15 bits, in which we had flags like carry, auxiliary carry, sign, bit, parity, directional flag, tag flag, interrupt flag, and overflow flag. So similarly, now for 80386, instead of 16 bit of flag register, we have how much? 32 bit of flag register. Out of which, can you see the first flag at bit 0, which is CF, which is carry flag. So if the result generates a carry, this flag will be be set to 1 or else it will be set to 0. If you remember previous, all the other bits which were empty, we used to put 0 there. But here in 80386, your only D1 has 1. Remaining all the other empty bits have the value 0. Okay. So since D1 value, so there is no function, but it will, the value inputted will be 1, not 0. In 8086, it was 0. Now flag number 2, what does it stands for? PF. What is PF? It is parity flag. So if your result has even parity, it will be set to 1. If it has odd parity, it will be set to 0. D3 does not have any function, so it will be set to 0. D4 is set to AF. What is AF? Auxiliary carry flag. So if and carry is generated from bit number 3 to bit number 4, the auxiliary flag will be set to 1 or else it will be set to 0. Again, D5 does not have any function, so it is set to 0. D6 is called as ZF. What is that ZF? It is 0 flag. That means if your result is 0, this bit will be set to 1. If your result is non-zero, it will be set to 0. 7th bit is SF. What is that SF? Sign flag. So if a number is positive, it will be 0. The value will be 0. If the number is negative, the value will be 1. Next is TF. What is trap? The TF, trap flag. So if the priority is highest with a trap, that means you have to look into that interrupt, which means what? You have to stop your current execution of a program, go and handle the interrupt. So if there is any trap kind of interrupt, this bit will be set to 1 or else it will be set to 0. Then your bit 9 is IF. IF is interrupt flag. So if there is any interrupt and if you as a user entertain that interrupt, it will be set to 1. But if you ignore that interrupt, it will be set to 0. The next bit is set to DF. What is that DF? Directional flag. So the bits, if they are accessed from higher to lower, it is set to 1. If they are accessed from lower to higher, it is set to 0. Then the next bit is OF. OF stands for overflow flag. So if your result is more than 32 bits, then this bit will be set to 1. But if your result is exact of 32 bits, it will be set to 0. Now, there is something new from bit number 13 to bit number 31. What are those? IOPL, NT, 0, RF, VM, and reserved for Intel. Now, what are all these? These are something additional with respect to 80386. Whatever we discussed so far were common with your 8086. Now, can you see from bit number 18 to bit number 31? They are reserved for Intel. Reserved for Intel means they will be 0 for 80386. They will be activated only when I change my processor from 80386 to any of the Intel processor, that is i3, i5, i6, i7. If I use those, at that time these bits will be used, that is bits from 18 to 31. But if I'm using 80386 processor, these bits will, the value of these bits will be 0. That means they are reserved for Intel. They will be activated only when an Intel processor is being used. Now let us see into the remaining bits, that is IOPL, NT, IF and VM. Okay. First is a virtual mode. Now what do you mean by virtual mode? We have a small part of a memory in the system called as a virtual memory. Okay. What is that virtual memory? If you remember in the first lesson, I had explained you. It is a part of your RAM memory itself, which will delete all your additional configuration files and temporary files which are no longer being used by the user. So if these files are not used by the user, they will remove that, system will automatically remove that files and create a space. So whatever space is being created by removing these system and configuration and temporary files, I call that part of a memory as a virtual memory. So whenever, again, since if it is VM, this bit will be set to either 1 or 0. Okay. Now, if a flag is set, it enters into 8086 virtual mode. That means if this value of this bit is 1, which means what? This register will be used, or this flag register will operate in a 8086 manner. In 8086 manner means it will get converted into a virtual mode of 8086, which will assume that your memory of the system is filled up and it is entering into 8086 mode, where all your 32 bits will now be working as your 16 bits. Why? Because 8086, everything operates in 16 bits. It does not operate in 32 bit. Okay, so this will be, if it is set to 1, that means you have to assume what, everything inside your system, that means your processor inside the system is going to behave as 8086, and everything will be of different names which will make your system much slower compared to 8086. Okay, is this clear? Yes or no?
Ma'am, can you repeat what you just
Are you
said?
all there?
Because your voice was lagging a bit.
Okay, what did I say? A VM stands for virtual mode. Okay, what is that virtual mode? Your virtual, it is nothing but a part of a virtual memory. Whenever this bit VM is set to 1, which means what, it is entering into an 8086. That means the system will operate as 8086, where everything will be changed from 8086, which will make your system slower. If this flag is set to 0, that means you are operating in 8086 mode only, where everything is in the 32 bits. Is this now clear?
Yes, ma'am.
Yes or no? Huh. Next is our F flag, which is nothing but the resume flag. So the next to VM is the RF flag. What does that resume flag means? It is used with a debug register. So if my computer has any problem, or if it has entered into a debugging mode means if it is checking or if it is debugging each and every line of a program, how will it intimate to the system? It will be intimated to the system by setting this particular flag. So if this flag is set to 1, that means what, my program is getting debugged. Debug means each and every line is being observed. If it is set to 0 means what, it is not going to perform any debugging. It will just execute the program entirely and generate the result to the user. Okay, so when it sets to 1, it will do the debugging, but if it sets to 0, it will not perform that debugging. Okay,
Ma'am,
the next is
ma'am,
INT. Huh.
ma'am, resume flag does the same thing as trap flag. No, you said in the last lecture, trap flag does the same thing.
Trap is interrupt. Don't forget in both. What is happening? My program has 5 lines. Okay.
Okay.
When I do debugging, what it is going to do? It will execute each and every line. It will check for each and every line. So all 5 lines will be checked. When it will be checked in the resume flag. What is trap? If you remember, I had explained you with a phone call. If my father calls, I might read that call, assuming that I am a lecture now. It might be not important. But if a principal calls, that is more important to me than giving a lecture. So that is what is trap. That means interrupt aaya hai and compulsorily I have to attempt that interrupt. I cannot ignore. That is what is trap.
Okay,
Are
ma'am.
you
Understood.
understanding?
Yes, ma'am.
Huh. It is interrupt enable. What is interrupt enable? It is set if the interrupts are recognized, else they will be ignored. So what is happening? When a program is running, there are many kind of interrupts also running. Some of the interrupts will be generated, some of the interrupts will never be generated. Interrupt will be generated, never be generated means what, recognized. मतलब क्या, कुछ कुछ interrupt system recognize करके user को बताएगा, but many of the interrupts will never be recognized by the system and they never be told to the user. So this flag interrupt enable will be set whenever the interrupts are recognized by the system and given to the user for solving. Then a user has a choice whether to accept that or to ignore that. Okay, so if it is generated from the system, this flag is set. Now interrupts are also of many types: programmable interrupt, software interrupt, user generated interrupt, so on. So these types of interrupts are enabled and disabled by using this bit. Okay, that is what is the INT bit. Okay, so this IF is the interrupt flag, which means what, whenever interrupt is recognized over here with the int, then it will be carry forwarded to if. अगर इधर ही int में ही interrupt recognize नहीं हुआ, so it will never reach to this if bit. Okay, so your 9th bit will be activated only depending upon your 14th bit. So if your 14th bit has recognized the interrupt, it will be transferred to the 9th bit, but if it is not recognized, it will be never be transferred to the 9th bit. Is this clear? That is what is interrupt enable. Then is the directional flag. So this we all know, it is used for string operations. From low to high, the bit will be set to 0. From high to low, it will be set to 1. Then can you see this called as IOPL? What is that IOPL? It is IO, that is input output privilege level. So whenever any IO kind of operations are performed, that is giving the input from mouse, giving the input from keyboard, accepting the output from monitor. So if any such kind of IO operations are done, this flag, that is IOPL flag, will be set to 1. So every time we are going to give the input, we are going to take the output. So this bit is always set to 1. Whenever the CPU is idle and if a user is also idle, at that time this flag will be set to 0. Okay. So that is what is IOPL, in input output privilege level. So if IO operations are performed, then it will be 1. If the operations are not performed, it will be 0. Is this clear up to here? Everyone?
Yes, ma'am.
Yes
Yes,
or
ma'am.
no? See, please give me the response because I do not know whether I'm connected or not. My internet, I do not have live connectivity. Okay. Next, we have nested flag. Okay. What is nested flag? It is used to check any other task is called from the current task or not. Okay. Now, do you know what is nesting? Have you come across the word nesting in C, C++? Yes
Yes.
or no?
Yes, ma'am.
Huh. You have loops like for loop, you have nested query like if, else, and all. You also have nested if. What is that? If ke andar if. That means inside one if, you have one more if. So and it will perform based on that nested thing. So similarly, when you write an ALP program, that is assembly language program, you have many queries and many instructions which are nested, but the instruction which is used are different. How you have loops, for loops, while loop, do while loop. Whereas in ALP, you do not have for, do while and all. You just have to use a command or instruction called as LOOP, loop. So that will identify there is a loop inside. Similarly, you have nested thing. What is nested? You have a loop ke andar loop, you have if ke andar if, like this. So whenever you have such nested queries, how are those nested programs being enabled or disabled? They are being enabled and disabled by setting 1 and 0. So if your nested flag is set to 1, which means what, your program is nested. If it is 0, means what, your program is normal and there is no nesting inside your program. Okay. Then apart from this, so this was all about your flag register. 32 bits, out of which bits from 18 to 31 are never been used. They will be activated only when you are going to use the processor called as Intel. If your virtual mode becomes 1, your entire system will work as 8086. But if this is set to 0, your normal, it will work as 80386 processor. Okay. And every operation you do, the status of that operation
Your
will
voice
be.
is lagging.
Can you hear me now?
Ma'am, your voice is fluctuating in between.
Am I audible clearly now?
Yes, ma'am.
Hello. So this was all about the
Ma'am,
flag
you are
register
audible, but
of
we have internet issues
80386.
because of the cut.
Okay, how much ever you can hear, you hear me now. Later you listen to the recording. Okay.
Okay, ma'am.
Are you all there? Huh. So this was all about the flag register of 80386. So whatever operation is happening in your 808386, all that operations will be reflected with this flag register. Clear? Now next topic is, we have one more register called as debugging register. So we have seen general purpose registers, we have seen segment register, we know about instruction pointer register, we know about flag registers. Your 80386 has something extra, or one more extra register, which is called as debugging register. What is this debugging register? You have total 6 type of debugging register. One of the value is set through this resume flag. ठीक है, अगर debugging करता है तो flag is set to 1 or else the flag is set to 0. So you have your resume flag also, which will be used with this debugging register, which will be used for debugging. But ये debugging कौन करेगा? It will be done by these registers. Okay. So how many such debugging registers we have? 6. What are those? DR0, DR1, DR2, DR3, DR6 and DR7. This is not and, it is 7. Okay. So we have DR0 से लेके 3 तक 4, sixth which is fifth one, and seventh which is sixth one. So we have total 6 debugging registers which will be used for debugging the program, and whatever debugging result is there, all those debugging results will be stored in this debugging register, and it will be reflected by using the resume flag. Okay, now what is the function of this debugging register? First, it will debug each and every line. What it will do if it has encounter a problem, they will be used to add a breakpoint to a program. Now what is breakpoint? Now what breakpoint means, what if suppose I have a 6 lines of my program. Suppose if there was a problem after the third line, that means on the fourth line there was a problem when I was debugging. So I will mark a breakpoint on line number 4. What will happen when I mark a breakpoint on line number 4? It will be assumed by the system that there was an error at line number 4. And whenever that problem is solved, I will start the execution of a program again, not line number 1, but from that breakpoint, which is line number 4. Okay. So the breakpoint are the address where the program should break and pass the control to the debugging routine. Which means what? 1 से 4 तक normal execution हो रहा था. 4th पे there was an error. Therefore, the execution stopped at 4. At that time, until the problem was not resolved, it did not continued with the execution. Once the problem has been solved, your CPU will not execute from the first line, but it will execute from that breakpoint, which is the line number 4. So the function of this debugging register is to debug the program and add that breakpoint, so that whenever the program is resolved or the problem is resolved, the execution will be started again from the breakpoint. Is this clear?
Yes, ma'am.
Yes or no? Okay. So what is the function of this register? It will be storing all the details of those breakpoints. Okay. Then next we have test register. What is this test register? We have 2 test registers, which are those TR6 and TR7. What is the function of this test register? They are used to test the memory. Which memory they are used to test? The paging memory. If you remember, 80386 has 2 memory management unit, paging and segmentation, correct? So if I am using a paging concept, how will be my memory tested? My memory will be tested by using these 2 test register, TR6 and TR7. Can you see something written as TLB? What is this TLB? Translation look aside buffer. Now, whenever your paging is used, that means whenever every data inside the memory is being stored in the form of a pages, what is happening? The pages which are required, only those pages are accessed. Suppose if I tell you, I give you a book of computer organization, the TechMath book, and if I tell you open chapter number 3, which is on page number 126, what you will do is you will directly go to 126. Will you search page number 300? No. Will you search page number 220? No. You will only search for the page number which I have asked for. So what is this memory doing? Whenever any program is executed, it will search for that program in your paging memory. जिधर भी वो program stored है, only that particular program will be loaded for execution. So if I have 10 programs, out of which I want to execute only first program, all the 10 programs are stored in my paging memory with some page number to access. So when I say to the system, execute program 1, it will not bring all the 10 programs in the memory. Unnecessary, it will not test the memory. It will bring only program 1. Why only program 1? Because only that was requested for a user for execution. So it will search for the page number of program 1, say suppose page number 107. It will go to page number 107 and bring the program 1. It will not touch any other pages, which is 100, 200, 300 and so on, where the other 10 programs are stored. So what is this TLB? That is what is translation look aside buffer. That means I'm looking at the values, I'm looking at the addresses, and then only I'm retrieving that much data. So it is used to test the TLB. Test the TLB means it is used to test the translation look aside buffer and only bring those memory or that data which is required for the execution. And where is the detail of this all testing done stored? It is stored in either TR6 or TR7, which are nothing but the test registers of 80386. Is this clear?
Yes,
Yes or no?
yes, ma'am.
Yes, ma'am.
Okay.
Yes,
So with
ma'am.
this, okay. So with this, we complete with the register format of, or the register organization of 80386. Okay, we had seen all the general purpose registers. Let me come to the diagram again. We have seen all this general purpose register. The function are same that of 8086. We have also seen the segment register, instruction pointer, status and control register. Apart from this, we also learned two new register, which were those debugging register and test register. Total two test register, TR6, TR7, and total six debugging register, TR0 to TR3, DR6 and DR7. Is it up to here? Now, next topic we will be starting is the instruction format. Now we know that program is there. Program is a set of instruction. But what are these instructions and how these instructions are written for a assembly language program? Okay, that we will be studying. So what is the format of an instruction? So to write any instruction, I have to follow the format. So what is that format? It is made up of two things, which is opcode and operand. Okay, what is the opcode? It is nothing but name of an instruction is called as opcode. But what is operand? It is nothing but the address, or it may be a data sometimes. Okay, so it can be address also, it can be data also, depending upon what type of instruction I am using. So let it be any instruction in the program. All the instruction will have this two format. One is the opcode, another is the address or the data itself, called as operand. Okay. Now let us see what types of instructions do we have. We have three address instruction. Okay. Now what do you mean by three address instruction? We have three registers. Can you see that? R1, R2, R3. Therefore, it is called as three address instruction. Instruction chhod ke, if I have three things inside it, it is called as three address instruction. Instruction ko chhod ke, I have three instructions, three values, R1, A and B. Therefore, it is called as three address. So if you see all of them, apart from addition and multiplication written, you have three registers everywhere. R1, R2, R3, R1, A, B, R2, C, D, X, R1, R2. So if you have three registers in the instruction, you call it as a three address instruction. Out of which this add is nothing but the opcode of your instruction format, and this R1, R2, R3 is nothing but the address, or it is called as operand. Okay, that is what is three address instruction. Then you have two address instruction. What is two address instruction? Apart from the opcode, you will have two operands, R1, R2, R1, R2, R1A, R1B, R2C, R2D, R1, R2, X, R1. Therefore, they are called as two address instructions. So how do I read them? Add the contents of R1 and R2. Add the contents of R1 and R2 and store the result in R1. Move the contents of A inside R1. Add the contents of B with the contents of R1 and store the result in R1. Move the content of C in R2. Add the contents of D and R2 and store the result in R2. Multiply the contents of R2 and R1 and store the result in R1. Move the contents of R1 into X. This is how I read two address instruction. Two address means I have two things or two registers or two address at my operands. Just a second. Okay, so this is how I read a two address instruction. Then next is Single address instruction. What is single address instruction? Add the content of X with the content of X and with the contents of accumulator and store the result in accumulator. So how do I read this? Add X. Why single? Because I have only one register. So I will add the contents of X with the contents of accumulator and I will store the result in accumulator. What is the next instruction? Load A. So since I have only one operand over here, therefore it is called as single address instruction. How do I read this? Load the instruction of A into accumulator and store the result into accumulator. Again, how will I read this? Add B. Add the contents of B with the contents of accumulator and store the result in accumulator. How do I read this? Store T. Why again single instruction? Because I have only one address or one operand called as T. So how do I read this? Store the value of T in the accumulator. So TAC is what? Store the value of T in accumulator. So you have three types of instruction, that is 3 address, 2 address and 1 address. If you have 3 address operands or 3 operands, it is called as 3 address. If you have 2 operands, it is called as 2 operands. And if you have single operand, it is called as single operand instruction. Is this clear up till here? Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. So we are now aware about the instruction format. We have opcode and an operand. So this instructions can be of 3 types: 3 address, 2 address and single address. Okay. Next is the instruction length. That means how much should be the length of an instruction. Okay, when I make this format, that format should be there in that particular length only. If it is not in that length, your system will never execute. Okay. So since it is 380,386, how much should be the length? The length should be of 32 bits. Why? Because your data and address bus can carry how many bits? Only 32 bits. So if your instruction is more than 32 bits, I have to use that data bus and address bus twice. But it is exactly of 32 bits, I will be making use of the bus only once. If it is of 16 bits, I will make only use of a 16 bits of the bus. If it is of 8 bits, I will make use of bus only of 8 bits. Okay. But normally the instruction length of 80386 is of 32 bits. And why it is 32 bits? Because your address and the data bus is of 32 bits. Is this clear? Yes or no?
Yes, ma'am.
Okay. Next is we have to look into certain factors when we design or when we decide about the instruction length. तो ये instruction length 32 bits कौन से factors पे decide किया है? Based on the factors which are listed here. First is the memory size, memory organization, memory transfer length and memory transfer. So depending upon the memory size of 80386, depending upon the organizations of the memory, depending upon the transfer length of the memory, where comes the data bus and address bus, and how much data it can transfer. Depending upon all these factors, I have decided that the size of my instruction length should be 32 bits. Why? Because when the factors memory size, organization, transfer length and transfer is of 32 bits, so my instruction should also be of 32 bits or lower to that. It cannot be greater to that. Even if it is greater, it would be handled, but in 2 different parts. Okay, in 2 different transfer. So these are the factors which I have to look upon before I decide the length of the instruction. Is this clear? Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So with this, we complete the remaining half part of the chapter. So we have seen today the register organization of 80386 and what is the instruction format of 80386. Tomorrow we'll be starting with the different types of addressing modes inside 80386. Okay. Is this clear, whatever has been taught today?
Yes, ma'am.
Yes or no? Okay, give me your attendance. Faizan,
Present, ma'am.
Hamza, Hamza. Muzammil.
Present, ma'am.
Tahir.
Present, ma'am.
You all are
Present,
chatting
ma'am.
while you are. What am I asking you? How can you people chat when I am into the lecture? Everyone has replied to some of the other messages on the group. How can you do that? That means you're not paying attention to the lecture and you are simply going to the background applications, no, which are there in your phone. See, this will not be affecting me. It is going to affect you all. Tahir.
Present, ma'am.
Viraj.
Present, ma'am.
Om.
Present, ma'am.
Yash Chauhan.
Present, ma'am.
Samarth.
Present, ma'am.
Devang. Devang. Absent. Reva. Soham.
Present, ma'am.
Jonathan.
Present, ma'am.
Sakshi. Sakshi. Om Inzatkar. Om Inzatkar. Mrudul. Ashna.
Present, ma'am.
Dhruv.
Present, ma'am.
Sanika.
Present, ma'am.
Mayuri.
Present, ma'am.
Pritesh.
Present, ma'am.
Hiteshi. Present. Aditya. Prayag.
Present, ma'am.
Moez. $25 was there. Who's 25? Akash. Okay. Sonia.
Present, ma'am.
Dishank.
Present, ma'am.
Is present. Okay. Aksh.
Present, ma'am.
Sahil. Nidhi. Both are absent. Pratham. Present. Shlok.
Present.
Present. Devang. Present. Drashti.
Present, ma'am.
Parth. Parth. Pooja.
Present, ma'am.
Krishnam.
Present, ma'am.
Nirmal. Pruthu. Pruthu. Harsh.
Present, ma'am.
Trisha.
Present, ma'am.
Ma'am, present. Ma'am, 40. Present.
Kenneth. Vignesh.
Present, ma'am.
Jay.
Present, ma'am.
Nishit.
Present, ma'am.
Parth.
Present, ma'am.
Varshil.
Present, ma'am.
Kenneth is present. Varshil present. Shakira.
Present, ma'am.
Taha.
Present, ma'am.
Disha.
Present, ma'am.
Arjun. Arjun. Prithvi.
Present, ma'am.
Keval. Keval. Sushant. Dhruv.
Present, ma'am.
Kush. Kush. Rudra. Gayatri, Gargi, Kavya. Okay. Nishant. $61. Okay. Yash. 62. Okay. Nishant present. Yash absent. Prem.
Present, ma'am.
Sharad. Shrey Gandhi. Tanmay,
Present, ma'am.
Naman. Okay. Tomorrow again lecture at 10. 29, 24, 29, 24. Okay. Tomorrow,
Ma'am,
see you on. Sorry?
yes. Can you post this recorded lecture of today?
Yes, I'll do that.
Okay, ma'am. Thank you.
Okay. Those who have got the owners, those who have got the videos ownership will be transferring it to me. See your test has been cancelled by Charu ma'am. Now you can see into the group if you want. Okay. See you all tomorrow.